All right, welcome to The Explainer. Today, we're unpacking a white paper that details what I can only describe as a massive paradigm shift in the world of artificial intelligence. We're talking about moving completely away from the era of those massive cloud-based AI behemoths that need absolute supercomputers to run. Instead, we're stepping into the age of incredibly efficient, localized models. Real, AGI-grade reasoning running right on your everyday consumer hardware. It's a total rethinking of how machine cognition works, and honestly, the architecture behind it is nothing short of brilliant. Okay, let's dive into this with a pretty big question. Have the current generation of massive language models actually hit a mathematical dead end? Because, the prevailing strategy right now is basically just brute force scaling. Make the model bigger, slap on more parameters, feed it more data. But the source material points out a really glaring flaw. These models rely on autoregressive depth, which is basically trying to predict the next word in a single, straight line. And the problem is, when they are confronted with high-entropy, highly complex reasoning tasks, they suffer what is called a catastrophic deterministic collapse. They just break down when the logic gets too tangled. And here is the staggering proof of that collapse. 0%. Literally zero. That is the accuracy rate of our current frontier models, models with hundreds of billions of parameters, when they're asked to solve Sudoku-Extreme puzzles. Think about that. Despite all that massive computing power, all those billions of parameters, they fail completely. It really just proves that simply making an AI bigger doesn't fundamentally make it smarter at complex reasoning. So here is our roadmap for today. We're going to cover 1. The Goliath's flaw, 2. David's sling, which is the math, 3. The hardware paradox, 4. Rules of engagement, and finally 5. The final showdown. Let's jump right into Section 1. The Goliath's flaw, the AI scaling dead end. Current autoregressive LLMs operate on a single-path trajectory. They scale by depth. But recursive reasoning models shift that entirely toward width scaling. Instead of a straight line, they explore k-parallel stochastic trajectories. What that means is they look at multiple possible solutions at the exact same time. This completely decouples cognitive power from raw parameter scale. You simply don't need billions of parameters if your model can think wide instead of just deep. Moving into Section 2, David's sling. This is where we look at the math over brute force. Now, what's really interesting here is the TQF solver. It replaces static matrix multiplications with dynamic state evolution. It literally treats the AI's thought process as a continuous wave function, kind of using Schrödinger-inspired dynamics. By using advanced math, specifically fourth-order Runge-Kutta integration, which, I know is a mouthful, the solver creates a seamless toggle. The system can switch instantly between strict, deterministic data grounding and nonlinear speculative brainstorming. I know the math sounds incredibly dense, but stay with me because the practical purpose here is absolutely game-changing. The Sanskrit Grassmannian is essentially a topological safeguard. It uses QR decomposition to map the model's data onto very specific geometric spaces called Grassmannian manifolds. You can think of it like assigning data to strictly enforced individual parking spaces. It ensures mathematical orthographic integrity. And the whole point of this? It completely prevents the semantic overlaps that trigger AI hallucinations. It quite literally stops the AI from getting its wires crossed. And to combat that deterministic collapse we talked about earlier, the engine uses Stochastic Latent Transitions, or GRAM. GRAM injects reparameterized Gaussian noise into the system. I really love the analogy used here. It gives the AI kinetic energy. You see, bad basins are basically mental ruts or suboptimal traps where traditional deterministic models usually stall out. By injecting this mathematical noise, the system literally breaks free from those traps. Plus, it uses persistent conditioning to keep all this wild exploration perfectly tethered to your original prompt. All right, Section 3, the hardware paradox, using SSDs as cognitive extensions. So we have all this advanced dynamic wave function math, right? The obvious question is, how on earth can this possibly run locally on less than 3 gigabytes of RAM? Well, the answer lies in treating your physical SSD storage as an actual extension of the AI's brain. Through a process called MoEfication, or sparse upcycling, massive parameters get zapped into tiny 30 to 50 megabyte semantic clusters. Using a 12-byte entry hash, the system achieves instant lookup complexity. Instead of completely clogging up your RAM, it treats your SSD like a highly organized library, jumping directly to the exact cluster it needs, instantly. And to put that into perspective, the speed is phenomenal, 5 milliseconds. By combining this modification with something called Fibonacci cubing tensor decomposition, which is a really complex name for a beautifully simple result, the engine drops that SSD cluster retrieval latency down to just 5 milliseconds. That is incredibly fast. It allows high-level cognition to thrive right on local consumer-grade hardware without the prohibitive lag you usually get from cloud servers. And this brilliantly illustrates how it actually pulls that off. To achieve jaw-dropping 50-to-1 compression ratios without losing fidelity, the architecture dynamically applies a massive taxonomy of distinct block classifications. It actively looks at the data, figures out whether it needs logical bitwise optimization or sequential stream encoding, and applies the absolute perfect method on the fly to shrink that footprint down to size. Moving to Section 4, Rules of Engagement. Strict rules for system integrity. Okay, so to keep this ridiculously fast, localized system from just unraveling into total chaos, the architecture enforces these 7 immutable rules. It essentially forces absolute architectural discipline. For example, downward imports only, ensures the logic layers never get tangled up. Strict runtime isolation keeps the backend code tightly quarantined. And my personal favorite, honest abstention. This means if the AI simply doesn't know the answer, it throws an abstention error rather than suppressing it and just making something up, which honestly is the ultimate cure for the hallucination problem we see everywhere today. And this strict discipline extends to the build process as well. The system's 10-phase rollout is guarded by rigorous validation gates at every single phase to ensure total system coherence. From the repo scaffold in phase 0 all the way to full integration in phase 6, you literally cannot move forward unless specific automated tests pass perfectly. But phase 7 is where it gets really strict. Phase 7 acts as the ultimate quality bouncer for the entire system. This is the math kernel benchmarking phase. Every single math kernel has to earn its place by proving superior performance against baselines. If it doesn't definitively improve the system, it gets removed, plain and simple. Only genuinely superior mathematical logic reaches the production pipeline. Finally, Section 5, the final showdown, benchmarking local AGI reality. Let's move to how this builds up during actual inference. When you ask the AI a question, it runs through the Q-head selection funnel. First, it evaluates 100 parallel stochastic trajectories. Remember that width scaling we talked about? Second, it executes an argmax selection to find the absolute optimal path among those 100. And finally, it projects that state via a lattice decoding transformer. This rigorously, mathematically, forces the AI to output the correct answer, or fundamentally abstain rather than hallucinate. And here is the mic drop comparison. On Sudoku-Extreme accuracy, standard frontier LMMs with billions of parameters hit a deterministic collapse at 0%. 0. The long MoA AGI bottleneck model, it hits 100% accuracy. Let's look at the parameter count. Billions versus just about 7 million. And the hardware footprint. Massive cloud server farms versus less than 3 gigabytes of RAM on your local machine. That is literally less memory than keeping a few web browser tabs open. We are talking about a 7 million parameter model mathematically crushing billion parameter behemoths. So the crucial point is this. The SHD-CCP protocol completely redefines test time scaling. This white paper proves, without a doubt, that strategic stochastic width definitively beats brute force parameter depth. By entirely rethinking the math, we now have a viable, highly accurate path toward running neurosymbolic AGI locally. Which leaves us with this final thought to chew on. The paradigm has shifted. The technology is mapped out. Are we finally ready to bypass the massive cloud hardware tax, step away from the stumbling giants, and embrace true AGI directly on our local devices? Thanks for joining me on this explainer. Keep asking questions, and I'll catch you next time.